Well, thanks for that very good overview, Barry. And what I'm going to be focusing on today is iron and some of the pitfalls, some of the challenges, and certainly the importance of monitoring iron and corrosion product transport. I'm going to talk about sample conditioning and some sample methodology. You're going to see a lot here that has to do with grab sample. As Barry suggested, grab sampling is not the ideal method. We really want to do something more online and continuous. However, since a lot of facilities are still doing grab sample, we want to make sure that if that's the only method available, it is at least being done properly. Because if you're not doing it right, there's little sense in doing it because you can be getting a lot of false information. So then we're going to move into talking about some of the other methods of analysis that are out there. We will talk about online technology, which can be very useful, and then finally finish up with validation. So sample conditioning, and I say assumptions here. It's not because these are not important, it's because they're very important. But most of these items on this slide are going to be addressed by the system integrator, the panel manufacturer, the engineering company that puts together the system that most likely you have at your facility. Doesn't mean it was done correctly, but we're assuming that these things have been addressed. If they have not, it's important to go back and take a look at them. Again, proper pressure reduction, cooling, having the right isolation valve, the sample lines, making sure that the length, the routing, the size, flow rates, all those kind of things are designed appropriately. Because if they're not, no matter how much care we take in sampling properly, we're not going to get a good sample. We don't have time to really spend on all of this, but again, we're making the assumption that all of these things are in place. What I am going to talk about here, and this is grab sample methodology, is a 10-step program. And this can be found directly in the IAP's technical guidance document on corrosion sampling. So there's a lot more detail there. And again, it's freely available to everyone, whether you're a plant owner, operator, consultant, water treater, whoever you are, it's available to everyone. So I want to go through this because I think it's real important if you are doing grab sample, that you do it properly. So first of all, using the correct bottles. HDPE is probably the best to use. It's not the only material, but it's really preferred for using grab sample with ultra pure water. You need to properly clean the bottles and caps, and the best way to do that is with ultra pure water. Most power facilities and a lot of industrial sites will have very good DI water available. So it's not like you have to bring in separate water. A lot of times you can use that water as long as it is very clean, pure, and in this case, free of any iron or copper products. Then what you do is you're going to add some concentrated nitric. And again, using high purity, you're going to add that in the amounts listed. What that's going to do is pretty much clean the bottle and prevent it from getting any further contamination. This one here might seem obvious, but it's not always obvious. Make sure there's no filters or strainers in your sample. I was at a site once, we're getting very low iron readings, in fact, too low, almost non-detect, and I said, this just doesn't sound right. Well, they went back and they looked and they find out that they had a filter right before we were sampling. So as obvious as this is, ask the question, double check, because if you're filtering out what you're trying to measure, you're not going to get a good sample. This is another one. open the sample line valve and establish sufficient flow and make sure it's flowing for a while. Now, a lot of water panels will have lines that are continuously running. That's ideal because what you don't want to do is go to a panel or go to a valve, open it up, and then take a sample. Opening and closing of valves and doing anything that disturbs that sample line is going to give you a reading and a sample that is not really representative of what's going through that tubing. So having a stable flow and making sure that the unit that you're measuring on has been stable for a while. That's a situation I've also encountered many times. Show up at the plant and we go to take a reading and find out the plant is just been put back online or is in the process of coming back online. That is not a stable condition. Maybe a condition that we're very interested in learning about, but that is not a stable condition at all. Okay, so now without flushing, and you might say, well, why wouldn't we flush the bottle with some sample? Well, we just did a special nitric cleaning. And if we're flushing it, we're going to take that protective layer that we've done to make sure that we're not going to get any contamination. So we're going to do this without flushing after we've gone through the procedure, fill the bottle, seal it, and then send it to wherever you're going to do the lab. It might be right in the same area. It might be in a different location. Now, I'm going to be talking about another procedure. So keep in mind that we're talking about two similar procedures here. And I might be somewhat contradicting what I'm saying here, but actually I'm not. So I'll try to point that out as we go forward. So again, when should that sample be analyzed? Well, as soon as possible. But normally, once you do collect the proper sample, it's going to be okay for a while, but you don't want to, delay too long so that if there is any significant corrosion product, it's not settling out. And then normally dispose of the bottle or make sure that it's cleaned properly before you go to reuse it. There's a lot of different methods for analyzing corrosion product transport. You'll see some here in black and some in red. The ones in black I'm not going to focus on for a couple of reasons. One, they are all grab sample methods. Two, they are ones not typically found in most HRSGs. You might find them in a nuclear facility, or they might be in a central lab that's part of your utility, but they're not ones that typically can be done right on site. And you'll also notice the limits of detection. AA and ICP, AES, 7 ppb, as you saw the numbers that Barry put up, that's really borderline, and for some applications, those are just too high. Now, the graphite furnace and the ICP mass spec, those are good. And again, very reliable methods, but again, they're grab sample, not typically going to be something that a HRSG facility can do on site. And so we're not going to be focusing on those. The ones in the bottom are ones, though, that may be used currently and ones that we want to talk about. Those are the B&W membranes that most of you are probably familiar with, corrosion product sampler, and then visible spectroscopy. We're also going to be talking about an online method using laser nephelometry. And those are the ones we want to spend some time on, because for a HRSG facility, those are probably ones that are going to be a lot more practical. So you've probably all seen this filter chart. And again, some utilities really rely on this. Again, it's a method that's been around for a long time. And what I'm going to say is that any method done properly is better than not doing a measurement at all. However, doing a measurement and not doing it properly is probably just as good as not doing it. So whatever it is that you're doing at your facility right now, if you do it properly, it's going to give you some valuable results. And you know, these the filter tests here are going to tell you if you've got iron. They're not extremely quantitative, but they're going to give you a pretty good visual and a pretty good idea of where you are on the spectrum. A corrosion product sampler. This is, again, a method used by a lot of facilities. What it does is it collects corrosion products, it quantifies the rate of corrosion, and it can be an effective method. It's certainly better than just doing a grab sample measurement. And so, you know, we put it up here as one of those methods. Here you will see kind of a schematic of that and some key steps. Basically, we're collecting particles on a filter pad, typically, you know, anywhere from a 0.1 to a 0.45 micron. And then further, it can also account for the dissolve fraction. And that's important, and we'll have more to say about that later. As Barry mentioned, if we're only measuring dissolved, we're missing the big picture. So in any kind of a test that we do, we need to be looking at dissolved and particulates. That's where we move into visible spectroscopy. And by doing a test and measuring at 562 nanometers, we're kind of measuring that maybe pinkish to purple color. And we'll talk about what that is and how that develops. But this is a colorimetric method. Again, it's a grab sample method. And it's so important that there be a digestion. If you're just grabbing a sample and looking at dissolved, you're missing most of your corrosion product. And as recent as last week, I was at a facility having this discussion. They were doing this analysis. They've been doing it for years, and they were not doing a digestion. So again, we repeat this over and over and over again because there's facilities not doing it properly, and they're getting a false sense of security. So what is this spectroscopic method? It's what we call, for real quick, we call it the Ferrozine method. And what the Ferrozine reagent really is it's a combination reagent. So it consists of a color developer that complexes with the ferrous ions, and it forms that pinkish purplish complex. That color intensity is proportional to the iron concentration. And we measure it at the wavelength that we've designated, and it works out very well. Now, what is the TGA? That's the part that gives it that distinct smell that everybody complains about. So you have to do this in a fume hood. The TGA is thioglycolic acid. It is what digests or gets all of the suspended iron particles into solution so that we can measure the total iron. And how do we do that? And we've done some work to determine, what the minimum temperature and time is, and pretty much 135 degrees C for 30 minutes reduces all of the iron, including any magnetite and hematite present. Then we use this Ferrozine method, and we can get a total iron. So now I'm going to go talk about, again, we're talking about a grab sample method, talk about the preparation of the sample cell. And what I'm saying here might be a little bit different than what I said about doing a grab sample, but in a lot of ways it's similar, but it's so important in doing this properly, because if not, you're not going to get a good analysis. So we talked about using nitric before. Now here, instead of using nitric, we're going to use the Ferrozine reagent itself. The Ferrozine reagent is a very low iron, so meaning negligible amount of iron present in it. So we put 8 drops of the Ferrozine into a 1-inch sample cell. We fill it with DI water. We cover it. We let it sit. That's going to clean our glass sample cell. Now the digestion vials. These are vials, and again, they may vary, but shown here is one of the digestion blocks with sample vials. The way to clean those is to put 8 drops of Ferrozine, 12 mils of DI water, heat for 24 hours at 135 degrees C. That's going to clean your digestion vials. Once you clean these vials, as long as you keep them closed, you don't need to do this every time you use them. Collecting the sample. Again, talked about that. You want to have a continuous stream. It's important that the tubing that you're taking this from is not disturbed. You're not opening and closing valves. You're not tapping on the tubing. And here I talk about rinsing the digestion vial several times with the sample before collecting. That's because this is glass. We're doing a little bit different type of cleaning. So rinsing with the sample is okay, whereas I told you not to do that with the bottles earlier. Once we digest that, we add 8 drops Ferrozine. We replace the cap. We mix it. We place it in the digestion block. We heat it. So we're basically doing the same thing to the sample as we did with the DI water as a cleaning of the vessel. So now we're putting sample in the digestion vial. We're adding the Ferrozine, heating it, digesting it, removing the vial from the block, and cooling it. Normally I put a warning here, and I didn't put it on this slide, but do not open that vial. For any of you that are doing the math, 135 degrees C, that's above the boiling point. So yes, this vial is under pressure. So you do not want to open it until it cools down, at least cool enough to the touch. Then we determine the reagent blank. This is, standard lab chemistry. You're going to place the sample cell in the spectrophotometer. You're going to zero it. You're going to remove that. You're going to, put some, and you're going to, transfer the sample cell. Well, actually here first, you're going to determine the reagent blank. So you're going to use some, remove the sample cell, put 8 drops of Ferrozine, remeasure it. What we're doing there is a little bit color due to the Ferrozine. So you're establishing the reagent blank here. The difference between your reading with only DI water and with DI plus the Ferrozine is going to give you the reagent blank. Normally that's going to be very small. You're going to subtract that from the actual reading of your sample. So you're going to put the sample cell in. You're going to put the digested sample in, take a measurement, and then you subtract that reagent blank from the reading that you had with your sample. So it's a very simple measurement. The other thing that I want to point out here is, I didn't mention, but you want to do several samples. I've been doing this for a long time, and I'll usually do 5 or 6 identical samples, and invariably one of those I'm going to get, and it's going to be off scale. Don't know how that happens, but you want to throw out any outlier. So again, we're working with very low ppb levels. It does not take much to contaminate a sample. So now I want to move and talking about online technology. This is really the way to go. This is how you are going to know what's going on in your process all the time and see what's happening with iron. And one of the ways we found we can do this is with a laser nephelometer. It's a very inexpensive, very maintenance-free method, unlike a lot of those other technologies that I listed. What is a laser nephelometer or a nephelometer in general? Basically, we're sending a light through a sample. We're looking at the 90-degree deflection. And some of you may be familiar with particle counters and say, well, what's the difference? Well, a particle counter kind of uses light scattering, more of creating a shadow. And that's been used in the past for monitoring a corrosion product. The downfall is a couple of things. One, it generally cannot see particles below 2 microns in size, whereas the laser nephelometer can see down to submicron particles. So first of all, the particle counter is probably missing some of it. The other thing is, I don't know if studies been done to indicate the linearity. And I'm going to show you here the linearity of the laser nephelometer when making iron measurements. And that's very important if we're going to try to quantify it. So again, with online technology, laser nephelometer, we have a single particle, we're not going to see it. But with several particles, which we typically have, we're going to be able to detect this even down to part per billion, single digit, 1 ppb, maybe even below 1 part per billion. Here's an example of an actual plant setup. We have a controller that's going to read out iron concentration, either in ppb, if it has the ability to take that equation that I'm going to talk about, put it in, or it's reading out in nephelometric units, or typically NTU or milli-NTU. How does this work? Typically, you're bringing in a 1/4-inch line. It can be from an existing sample panel you have. If not, we have to make sure that all those assumptions we said early on are being taken into account to have a good sample. And then we have our laser nephelometer. Here's the linearity. This is showing the nephelometric correlation, both for hematite and magnetite. Hopefully, if you're a HRSG, you're not seeing black samples, you're seeing more red samples. But in reality, there's a combination between the hematite and magnetite. And that is why we have to do a site evaluation here. And you see that while the lines are all very similar, there's somewhat of a variation, and that's due to the somewhat of a variation between the hematite and magnetite ratios. Very easy to do a correlation. You would take a grab sample either after the nephelometer or at the same sample as a nephelometer. You'll do that laboratory reading. You'll get a reading in ppb. You look at what your nephelometer is reading. In this case, it's reading 16 milli-NTU. I received a lab reading of 3.4 ppb. We put that into our spreadsheet here, which is available. It's a very simple spreadsheet, but something that I could send to anyone that's interested. Creates an equation. Put that equation either into your DCS or into your controller if it's a smart enough controller to have that capability. And now you're going to be reading out in ppb iron continuously with a very low maintenance online surrogate analyzer. Here's kind of a sample showing, what that looks like. It's showing what's going on with the turbine, what's going on with the steam flow, and showing you the both the calculated and the laboratory iron, as well as that nephelometric, which we're calling turbidity here, showing how it all tracks very well. And I realize I sped through this very quickly, but there was a lot of important information that I wanted to make sure that I was able to share. So finally, with any program, we should validate it. We need to, again, make sure it's linear over the relevant measurement range. That's very important. We need to look at the systematic error, the accuracy, repeatability, reproducibility, and make sure that the detection limit is within what we're trying to measure. Well, thank you for your attention, and I turn this back over to Barry.
Thanks, Ken. Excellent introduction to some of the simple things we should be doing in the plant, and exactly on time at 25 minutes. Thanks very much. And we have one question here already, and we'll see if any other come in. So, Scott, can you maybe open the line for Wayne Troop? Or I can just read it out if necessary.
Yes, good morning. Thank you for taking my question. My question that I posted was, with flexible operation these days, it's difficult to have a system that runs any longer than maybe 10 hours in some of our circumstances. And so getting a sample that has been collected from a system that's been online a sufficient amount of time becomes difficult. But I think that Ken kind of explained that multiple samples are the best way to go about doing any kind of analysis. So I think he answered my question as he was speaking.
Okay, good. So yeah, Ken, is that okay?
Yeah, I'm fine.
If I'm allowed, I have a comment, Wayne. The thinking now is that for these flexible units and fast start units, it's not necessarily the absolute number that matters. And what we're trying to do, and there is a white paper on this from IAPS if you're interested, is look at the decay profile that takes place and then fix that onto the map. And if Scott can just let me share my screen, I can show you exactly what I mean. So Scott, yeah, thank you. And so Wayne, this is taken from the IAPS white paper, and you can see here. So here is this blue curve right here is the one that Ken was talking about using some proxy method. And then, so you can see when you start up here that the iron levels are very high, and you can plot that onto a decay map like this. And where you ideally want that profile to be is in this green area at the bottom. And so this process is in development at the moment. And so you can see here's an example from a Danish combined cycle plant superimposed upon this decay map. And so you can see that same profile for the proxy iron levels. And what you really want them to be is in this green area. And as Wayne, as you probably know, many of these situations when you bring a unit back from or on a fast start or a flexible unit would be in this red area, and the decay would be over here. And by improving some of the shutdown and operational conditions, you get it down to this sort of level. So just a few extra things on what Ken was indicating.
Bruce McKenzie has his hand up.
Okay.
Hey, how are you? Thanks for this. So I just did want to talk about first. You should be able to hear me. Can you hear me?
Yes.
Yeah. Okay. So because this is the issue that I think our industry is seeing, right? You know, I'm at a 2-on-1, 2 power block, HRSG combined cycle. And, you know, 2 or 3 years ago, we were running like a peaker. We were starting and stopping 3 times a day. All right. And now we're still running like a peaker, but it's more like starting daily, shutting down at midnight. And so just to sort of carry this on, you know, this idea of getting steady state conditions for sampling, it just appears to be like non-existent today in our industry. I don't know. Is that what everyone sees? I mean, even when we start up, you know, we're on one-on-one, we go to 2-on-1, we go back to 1-on-1, and then, you know, we're chasing solar throughout the day. We're never at a steady state power.
Yes.
And so this whole thing about sampling at steady state conditions, but the fact is too that when we sample, this is our condition, right? Yeah, we're not at optimal sampling conditions, but the fact is when we sample, that is what's going on with our units. So any comments on that? Sorry to just sort of.
No, Bruce, that's exactly, that's exactly what I was just alluding to, and why we're trying to introduce these new processes. I don't want to repeat it again. Ken, do you have anything else to say? But I think we agree, right?
But absolutely. And like Barry said, you know, it's not so much the actual number, but watching the trends. And it's more important that maybe like when the correlation that I pointed out is that you do that during a steady state to make sure you're getting the correct equation. But then after that, of course, yeah, we want to see what's going on with that's real life, the starting and stopping. And that's why grab sampling can be kind of, it's hard because you don't know what's going on when you're pulling that sample. That's why having some sort of an online monitor, even if it isn't a true iron analyzer, if it's a surrogate method, is going to show you that trending and give you some idea of what levels you're at is so important. In fact, it's probably more important to watch those trends than know exactly what your number is, because when you're getting peaks, you don't care what those peaks are. It's a problem. When it's a flat line, then you might want to know, am I at 2 ppb or 5? But when it's not flat line, like you said, which is a lot of the situation, you want to see what's going on. So yeah, I think we're all saying the same thing.
Yes. So yeah, thank you, Ken.